Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and in the last lecture I introduced a mathematical model for triodes. That mathematical model is fairly complicated to deal with, so in this lecture I'm going to develop a small signal model for triodes that linearizes that nonlinear model. The 3 halves in the power of the equation for the current flowing through the tube is pretty complicated to deal with. In the case of bipolar junction transistors, we have an exponential property, and we often approximate the base to emitter junction as having a so-called diode drop of somewhere between 0.6 and 0.7 volts. This 3 halves gives much too gentle of a slope for such a model to be useful. In the case of field effect transistors, we have a square law that's amenable to using the quadratic equation. Again, this 3 halves, aka 1.5 power, isn't really convenient to deal with analytically. So graphical techniques are going to dominate in this course. And this is a subject that is steeped in tradition. And back before computers or even desktop calculators were common, graphical techniques dominated engineering in general. So we're going to draw a lot of lines on plots and see where they intersect. Remember that for proper operation, the plate to cathode voltage needs to be positive. And it's very important that the grid to cathode voltage not be positive. This is an extreme failure condition. Let's talk about that grid to cathode voltage for a second, usually just called the grid voltage. I'm going to assume that the actual grid to cathode voltage is equal to some sort of DC bias, and that DC bias represents a quiescent operating point, usually called a Q point, that's some fixed voltage that we pick when we're not putting any audio into the circuit. And we're going to suppose that we're going to add to this DC bias some small signal variation that's the actual signal, that's the actual audio that's going into the circuit. The total signal we're going to represent using a lowercase main symbol and then capital subscripts. The DC bias is going to be represented with capital everything, and the small signal variation is represented with lowercase everything. And we could write similar expressions for the plate to cathode voltage and the plate current, which is the same as the current flowing through the cathode. I picked up this notation from my colleague Marshall Leach. I'm sure there's other authors out there that use the same kind of notation. When I first taught this, I had a tendency to put little tildes on top of the small signal to try to indicate the wiggly variation, but those tildes got tedious. So now I just stick with this approach. It does take a bit of time to get used to. Here are the transconductance curves, aka transfer characteristics for the 12AX7 from the General Electric datasheet. These plot the plate current versus the grid to cathode voltage, and what I'm interested in here is the transconductance, namely the slope of this curve that shows how the plate current changes relative to a change in the grid voltage. So here's the plate current equation for the situation where we do in fact have current flowing. And if we take the derivative of the plate current with respect to VGK, we can get a quantity we can define as G sub m, the transconductance. So taking the derivative, the 3 halves in the numerator comes down in front as a factor of 3 halves. And then we take the derivative of what's inside the parentheses here with respect to VGK, the VPK goes away. And when we take the derivative of this 3 halves, we lower that power by 1, giving us a square root. I'm going to always assume that our derivatives are evaluated at some quiescent operating point. Namely, we take these VGK and VPK expressions here, and we plug in the fully capitalized versions, namely some DC values of operating points that we've chosen. Suppose we want to operate our circuit using a DC bias point of VPK of 250 volts and a plate current of 1 milliamp. If we take a look at the graph here, we can take this 250 volt curve, take a look at the 1 milliamp line, trace it over, get a point, and then trace that down to find that our quiescent grid to cathode voltage is minus 2.1 volts. The transconductance is the slope of the curve at that point, and let's see if we can estimate that slope from the graph. So we need to pick a small line segment that reasonably fits the curve. We can't make this line segment too long, or we're actually getting into the point of the curve where it starts bending and we're not getting a good estimate of the slope there. So here we're going to estimate the transconductance by taking some points around that operating point. Let's say we were to look at the plate current of 1.2 milliamps. If we trace that intersection down, we get a grid voltage of minus 2 volts. Let's look on the other side. If we were to look at the plate current of 0.8 milliamps and then trace that down, we would get a grid voltage of minus 2.25 volts. So we can now take some finite differences and write 1.2 minus 0.8 milliamps in the numerator and minus 2 minus 2.25 volts in the denominator. Of course, the minuses cancel here, giving me a plus, giving me 0.4 milliamps over 0.25 volts, giving me 1.6 millimhos. Mhos being the reciprocal of ohms. This is a unit of conductance, which is the reciprocal of the unit of resistance, as represented by this upside down omega. In the last lecture, we looked at another way of plotting these kinds of curves called either the plate characteristics or, as my colleague Marshall Leach liked to call them, output characteristics, where now we fix a particular grid to cathode voltage and plot the plate current versus the plate to cathode voltage. The slope of one of these curves, the change in the plate current relative to a change in the plate voltage, that defines a plate conductance, which I'm indicating here with a G sub P, and that's the derivative of this expression with respect to the plate to cathode voltage. When I take this derivative, once again, the 3/2 in the numerator comes down as a constant in front. But now, since I'm taking the derivative with respect to VPK instead of GK, I don't get a factor of mu out in front that I had previously, but the square root expression is the same. People don't use GP very often. They usually use its reciprocal, the plate resistance, and that's the derivative of the plate to cathode voltage relative to the plate current. So that's just the reciprocal of this expression here. And here we now have the reciprocal of a square root as indicated by this minus 1/2 power. Now, if you're one of my Georgia Tech students, you should follow the calculus. If you're somebody from the more general community who's watching this and isn't quite following the calculus, don't worry about it. That's okay. We're not actually going to use these kinds of expressions very often. We'll mostly just be looking up values on graphs. Now, if you go back and look at this expression for the transconductance, you'll see the only difference between this and the plate conductance is this factor of mu. So we can write the plate conductance as the transconductance divided by mu, or in terms of the plate resistance, we can say that mu is the transconductance times the plate resistance. I want to emphasize that this plate resistance is a dynamic quantity that's part of our small signal model. It doesn't, for instance, represent the resistance of the wire inside the tube that's connecting the outside of the tube to the plate itself or something like that. So let's take a look at some output characteristics. Here I have our choice of a quiescent plate current of 1 milliamp and a plate voltage of 250 volts. And if we intersect these, we see that we do get a grid line that's somewhere around -2 to -2.5 volts. It should be at this -2.1 volts, which is what we found was our operating point previously using the transconductance curve. But we don't actually have an explicit curve for that, VGK of -2.1, so we have to kind of eyeball it a bit. So we're going to try to draw a little line segment that's sort of running parallel to these curves, and that is kind of in this ballpark. So our plate resistance is going to be the change in the plate voltage relative to the change in the plate current. So let's make some offsets and try to compute some values. So let's say we go up from 250 to 260 volts, If I then trace left, that corresponds to a current of 1.15 milliamps. And if I go down the other direction and look at 240 volts and trace that across, I get something like 0.85 milliamps. And these are all values we're computing by eyeballing the curve. So we're not looking at computing perfect values. So we can compute some finite differences. I have 260 minus 240 volts over 1.15 minus 0.85 milliamps, giving me 20 volts over 0.3 milliamps, which computes to around 66.7 kiloohms. So we've looked at some small signal parameters that relate either the plate to cathode voltage to the current or the grid to cathode voltage to the current. Now we're going to look at something called the amplification factor that directly relates the voltages. So let me take that triode formula, divide both sides by k, and take both sides to the power of 2/3. Now, let me take that expression and rearrange it a little bit. So I'll take this mu gk term, move it over to the other side, and then swap the sides of the equations. So now I have an expression for VPK in terms of the plate current and VGK. If I take the derivative of VPK relative to VGK, well, that just gives me a minus mu. Okay, well, that's interesting. So what is mu? Mu isn't just some random parameter. It means something very special. It relates changes in the plate voltage to changes in the grid voltage with this minus sign. So mu is very different than the GM parameter and the RP parameter we looked at previously. Mu appears in the original triode formula. It's sort of a rock. It's a fulcrum between which the transconductance and the plate resistance are balanced. Again, we're not really going to use this formula very often, if at all, partially because although mu is a parameter you can find on the datasheet, k isn't. So if you really want to use this formula, say to do some sort of SPICE simulation, you would have to do some sort of parameter fit to the data on the datasheet, or maybe get a real tube and collect some data from it, and do a curve fit to find k. Now, mu is given on the datasheet, but as a sanity check, let's see if we can estimate mu from the graphs. So here's one of those transfer characteristic graphs, and what we'll do is we'll approximate mu as being a finite difference of the plate to cathode voltage over a finite difference of the grid to cathode voltage. So here's our operating point, a plate current of 1 milliamp, and we have a grid to cathode bias point of minus 2.1 volts. And the easiest thing to do here is to actually look at the curves that are drawn on the plot for us already. So here we have one at 200 volts, and here we have a plate to cathode voltage of 300 volts. And we can take the intersections of those curves with our current point here of 1 milliamps, and then trace that down and find grid to cathode voltages of minus 2.625 and minus 1.625 volts. So we see that we have a difference of 100 volts in the numerator and conveniently a difference of 1 volt in the denominator, giving us a value of 100, which is what we find on the datasheet. Now, we could also try to estimate mu using one of these output characteristic graphs. So here we have our 1 milliamp and our 250 volt bias points. And the easiest thing to do here is to grab the grid lines that are closest to it, namely minus 2 and minus 2.5 volts. And if we intersect our 1 milliamp line with those two curves and drop down, we see that we get plate voltages of 240 and 290 volts. Plugging in those values, we get a finite difference of 50 volts in the numerator and 0.5 volts in the denominator, which gives us 100. So here's another graph from the 12AX7 datasheet. This shows mu, the transconductance GM, and the plate resistance RP as a function of the plate current. Now, I should emphasize that this is only valid for the particular plate to cathode voltage of 250 volts, although Mu is pretty consistent over a wide range of plate-to-cathode voltages, and GM and RP don't change a whole lot for different plate-to-cathode voltages. But I do want to make that caveat. The vertical axis units are a little bit confusing. For the transconductance, GM, you want to look over here on the right, and here things are given in micromhos. As far as the amplification factor mu goes, for that you want to look all the way on the left, and those, of course, are unitless. Now, for the plate resistance, you want to go to the left, not all the way to the left, and here they're listed in terms of ohms. So throughout this lecture, I've used a plate voltage of 250 volts for my bias point. And that's not a coincidence. I picked that because it matches this graph. All right. So with that in mind, let's see what happens at our bias current of 0.1 milliamps. If I look at mu, well, notice that it's nicely 100 through most of its range. Now, it does drop a little bit at very low plate currents, and this is why you can't really use this mu of 100 when you're computing what the cutoff voltage would be. We talked about that a little bit at the end of the last lecture. To figure out the cutoff voltage, you pretty much just have to eyeball it from the various curves on the datasheet. Intersecting our vertical line with the GM plot, we get a transconductance of 1480 micromhos. And if we intersect our vertical line with the RP plot, we get a plate resistance of 68 kiloohms. Now remember that GM times RP should equal mu. So if I take these values and multiply them together, I get 95.2, which isn't exactly 100, but it's pretty close. And remember that I'm eyeballing these values off of ancient graphs. Now, remember that earlier in the lecture, we estimated RP and GM by taking finite differences from curves found on other graphs on the datasheet. And if we compare what we have here to what we found before, we previously computed GM as being 1600 micromhos. That's pretty close to the 1480 we found here. And we earlier estimated our RP at 66.7 kiloohms, which is pretty close to the 68 kiloohms. So close enough for rock and roll. So the point of computing all of those properties is that we can now create basically straight line approximations to these complicated curves where these straight lines are as close of a fit we can get around a certain bias point. So we're going to characterize our plate current in the small signal space as being the derivative of the plate current with respect to VGK times our small signal VGK plus the derivative of our plate current with respect to VPK times our small signal VPK. And again, there's an assumption throughout I'm using that these derivatives are all evaluated at the DC bias point. So we've defined these derivatives as GM and GP, although it's not very common for people to use GP, so we're going to substitute 1 over RP. By Kirchhoff's current law, currents in parallel add. So I can make a model for the circuit that is 2 components in parallel. I have a current source that's GM times VGK in parallel with a resistance RP. Now, under proper operating conditions, there's no current flowing through the grid, so I just sort of wrote the grid voltage out here kind of hanging out by itself. And this is a perfectly fine model. You can use it if it's convenient. It's by far the most commonly used model for transistors. But for vacuum tubes, there's another model that's equivalent and arguably a little bit more natural. Instead of thinking of the current flowing through the tube, let's think about the plate-to-cathode voltage. I could characterize the small signal plate-to-cathode voltage as being the derivative of VPK with respect to IP times IP, plus the derivative of VPK with respect to GK times VGK. Now, by the definitions we've had previously, I could substitute those definitions in and write this as RP-IP minus mu VGK, where IP and VGK are our small signal quantities. By Kirchhoff's voltage law, voltages in series add. So I can create a small signal model that consists of a resistance Rp and a voltage source mu VGK, where I have to be careful to get the sign right because there's a minus sign here. So the minus sign's up here running opposite of our usual plus-minus convention. So with the plus-minus here, we have everything matching up for Ohm's law with the current arrow going that way according to our usual passive component convention. And as a quick reminder, all of the derivatives here are implicitly evaluated at our bias point. So we have two models to choose from, and for triodes we generally choose from the model on the right because mu is a parameter that's more intrinsic to the nature of the triode. It shows up in the original triode current formula, and it's the parameter that's consistent over a wide range of currents. This contrasts with pentodes. We'll look at pentodes later in the course, and there we'll see that for pentodes, this parallel model will be a little more natural. You can apply a source transformation to either model in order to get the other one. Notice this model doesn't have any time-dependent, aka frequency-dependent characteristics. Later in the class, we'll look at models that include parasitic capacitances between the different terminals.